All right, so we're gonna go over what's called weighted linear regression. The idea here is if you're gonna fit your data to a straight line, there are some data points that may be more reliable than others, and you want to give them more weight. And by default, when Excel does linear regression, it doesn't do that. It just gives equal weights to all the data points. So that's what we're going to learn how to do today. We'll do a weighted linear regression. So this is the link to the computer activity. So if you click on that, it brings up a Google Drive file, a PDF file on Google Drive, and this is what you'll see. All right. And we'll continue to use the same, uh, we, I already created a template for you, an Excel template, and we downloaded that earlier for our data analysis for the stats template and for doing Q-tests. So there's a tab here for doing linear regression. Okay, so here's an example. Let's say you have 4 data points collected at x equals 20, 40, 60, 80, and y values here from 172.86 to 213.91. Okay, so this is our data right here. This is where we tabulate our data. And then here we have the weights. This is where we enter the weights. And then here is where we're going to calculate the y for the fitted line, the best fit line. This is not, you can't use the linear trend line on Excel because the linear trend line on Excel is for unweighted regression. When all the weights are 1, the trend line you get is what you'll see when you do. That's what gives you the trend line that Excel generates. Okay, so we're going to manually calculate what our best fit line based on the results of this calculation. Okay, we're going to compare that with the output, the unweighted regression that Excel does, and that's what comes out from the LINEST. Okay, the LINEST function. So we're going to do this, work on this together, create this template so that later this semester, all you have to do is modify your data and your formulas for your weights. And actually just your data and your uncertainties right here. And all of these formulas that are cells that are highlighted, you just automatically update. So that makes things a lot easier for you. Okay. Did I record this? Yeah, I did record this. Okay. All right, so let's go back to the handout. So linear regression. As I said, the method that's employed by Excel for determining the slope of the best fit line, not just the slope, but the y-intercept as well, is called least squares regression, okay? Least squares regression. Why is it called least squares regression? Well, in this method, the slope M and the y-intercept B of the best fit line is obtained by minimizing the sum of the residual squared, SRS, sum of residual squared. Excel refers to this as SSRESID, SS resid. That means sum of the squares of the residuals. Okay. This is also commonly referred to as the chi-square for your data. So what's a residual? A residual is just the difference between your experimental value, in this case, y sub I, and the calculated value from the best fit line. So mx x sub I times b. So m times your experimental x plus b. Your m and your b are unknown, but you determine it from your data. That's the slope and the intercept of the best fit line. So the difference between the experimental y and the y for the best fit line is called the residual. So you square all of those. You multiply each one of those by a weighting factor, W sub I, and then add them all up. So you get the sum of the weighted squares of residuals. Okay, so that's SRS. Now, when Excel does LINEST, it just says all of these W's here for all the data points to 1. So LINEST, linear regression with Excel, is unweighted. Okay, so this assumes you have data points x1, y1, x2, y2, all the way to x sub n, y sub n. Now, the idea, like I said, for weighted regression is that some data points are more reliable than others. So you get more, you give more weights. bigger weights to the more reliable data points. And how do we minimize the value of the SRS? Well, why do we want to minimize the SRS? Notice that SRS really tells you how the data differs from the best fit line, right? How the experimental data differs from the best fit line. So the best fit line should be the line that differs the least from the experimental data. That's why you minimize your SRS. And the way you do minimization from calculus, you just take the derivative with respect to the things that affect whatever it is you're trying to minimize. In this case, your M and your B. So take the derivative, partial derivative of the SRS with respect to slope, set that equal to 0. Take the partial derivative of the SRS with respect to the intercept, set that equal to 0. We're not going to go through the derivation, but from these two equations, you can get the formula for M, and you can get the formula for the B. Okay? And like I said, in LINES, the LINES function in Excel, you give equal weights of 1 to all the data points. So all the W sub i's would be equal to 1. But if you know the uncertainties in your Y values, your experimental Y values, the uncertainties are delta Y, let's refer to those as delta Y, then you can set your W sub I, the weight for that data point, to be 1 over the square of its uncertainty. In other words, the smaller this uncertainty is, the bigger the weight you're going to give to your data. It's got less uncertainty, then that should be more reliable, right? So the thing is, you cannot use LINES if you want to do weighted regression. So we're going to have to manually set up on Excel how to do weighted least squares regression. But once we got it set up, all you have to do is reuse that template for future calculations. So in the formulas that we are using here, we are assuming that there are no uncertainties in X, or that the uncertainties in X are very, very small compared to the uncertainties in Y, and that the random errors in Y are normally distributed. We talked about normal distribution last semester. So we can do a weighted linear regression using these assumptions by doing the following calculations. The first thing you're going to do is calculate the sum of all the weights, okay? So you just add up all the weights. Let's do that for the Excel file that we have. Have you opened your Excel file yet? Are you still with me? Tatiana, Caitlin? Okay, you're still with me. All right, you're using chat. Since there's just two of you, you can unmute your mic if you need to communicate. You don't have to use chat. It's a little hard for me to keep track of what's popping up in the chat since I don't get a cue that something doesn't easily show up on my screen that you type something. Okay, and feel free to interrupt at any time. So let's calculate our, first of all, okay, here's our data. We have 4 data points, right? So we're gonna set it up so we can calculate the number of data points. So what would be this formula? It's gonna be equal to count. We're just gonna count all the X values. So right here, okay? Or you can use B4 to B7, it doesn't really matter. Okay, so that's gonna be our number of data points. Okay. In case you're wondering what this 0 and 100 are, I will explain that later. Okay, and it's gonna give you a warning that it's omitting adjacent cells. We intended to do that, so we're just gonna ignore that error. It's not an error. Okay. Now, like I said, S is the sum of all the weights. So what formula would you use for that one? So for now, let's just put a weight of 1 for everything, okay? We're gonna put a formula for the weights later, but for now, let's just put a 1 there. Actually, no, sorry. It's gonna be equal to 1 over delta y squared, correct? So our weights again is gonna be equal to 1 divided by delta y squared. So you don't have to modify this anymore after we've completed this template. So I'm just gonna copy that down. So all the delta y's are 1, they all have the same uncertainty. It makes sense that they all have the same weights. All right. So S is going to be the sum of all the weights, so sum of these numbers. Okay. In this case, it's going to be 4. There's 4 data points. Each has a weight of 1. You can see S is 1. Now, that happens. Let's say my delta Y here is 2. Then notice that this has a bigger uncertainty. This data point has a bigger uncertainty of 2. So it's got its weight is only a quarter of the weights of the others. Okay, 1 over 2 squared is 1/4, which is 0.25. Let me just set that back to 1. So that's how you calculate the weights. Oh, let me just do this again, 2. And you'll notice it doesn't have as much weight, but the S right here is now not 4 anymore. It's 3.25. 1, 2, 3, 3.25. Okay, so let me just reset that back to 1. That's how we calculate our S. All right. Next thing we need to do is calculate SX, which is the sum of all the X values, but it's a weighted sum. So you give more weights to some of the X values. So that's S sub X. So how do I do that? Right here, SX. So what I can do is I can use what's called, let me see. It tells you how to do it. Or does it? Let me see if I gave you specific instructions on how to do it. Here. Calculate S sub X. You can use the sum product function, okay? So sum product, and how do you use sum product? The whole idea here is we're gonna take the product of the weight and the X. So what we're saying is this weight 1 times X1 plus weight 2 times X2 plus weight 3 times X3 plus weight 4 times X4. I'm basically taking a dot product of these two. It's called sum product at Excel. I'm just going to say that's equal to sum product, open parenthesis, of this number, and that's the weight, and that's the X. So that should be your sum product. Okay. So 1 times 20 plus 1 times 40 plus 1 times 60 plus 1 times 80. That should add up to, well, that's 60, 60, 120, 200. Note that if I make this weight equal to 2, look what happens. This now is 220 because this is weighted twice. Okay, let me undo what I just did. I don't want to do that. I'll keep this to the original formula, which is 1 over 1 squared. Okay, so that's S sub X. How do I do S sub Y? That would be the weighted sum of the Y values. Okay, so the weighted sum of the Y values. So let's calculate that. This is going to be equal to sum product, open parenthesis, the weights, and the Y values. Okay, so this is basically this number times that number plus this number times that number plus this weight times that Y plus this weight times that Y. So that's SY. All right. Now let's calculate our mean x values. The mean x values is the sum of x values divided by n, but since this is a weighted mean, it's the sum of the weighted x values, weighted sum of the x values divided by the sum of all the weights, okay? So this is right here. The mean x values is s sub x over big S. So this is going to be equal to s sub x divided by s. All right. So that's 50. That makes sense, right? Average of 20, 40, 60, and 80 should be about 50 if they all have the same weights like we have here. The mean y value, the weighted mean of the y value is s sub y over s. Okay, so weighted sum of the y values divided by the sum of all the weights. So this is going to be sy divided by s. So 193.98. Okay, still with me? I'm going to give you time to get caught up. I'm going to pause this recording. Actually, I'm going to stop this recording. Remind me to start it again when we resume. So for now, I'll let you get caught up.